Okay, you did it. You're at your last new Delta Math lesson of your AP Calculus career. Take a second to wipe away the tears that this is the last one, and also pat yourself on the back. If you're at this point, it's likely that you've been crushing it all year. I'm really proud of the work that you guys have done. And this class is a beast. It's a lot of content. And the fact that you got through all of it is an accomplishment. Okay. We're still in the 3D world for this lesson. But the setup is a little bit different. So I want you to ignore the text for just a second, except for this part. Each cross section perpendicular to the x-axis is a square. Okay. So imagine that you're an architect, you're designing buildings, and imagine we're looking at the floor plan. Like we're looking like straight down. You're making some weird pointy hallway. You're making like a nice curvy modern building with dramatic curves. Okay. So this blue region, this is R, this is the floor. And this hallway is square all the way down. So what that means, right, is my first square, and it's impossible to draw it correctly because I'm looking straight down at it. We wouldn't be able to see these squares. But this first square is going to be very large, right? So this would be kind of the entrance to the hallway. And as you walk down it, it gets smaller. So I think there was a Willy Wonka hallway like this, right? So that's what we're making. It's quite dramatic. Okay, so we need to find the volume of this hallway as it shrinks and shrinks and shrinks down to nothing. And that's obviously not the only application of like architecture. You can use a similar method to create all sorts of crazy shapes. So you can imagine like if you're manufacturing things and you need to know the amount of material that you're using, you might use something like this. We're going to use really similar logic to our rotational solids. But notice there's no rotating happening here, right? Instead, we're going to use just the general fact that the volume of this shape is going to be, well, it's going to be the area of each square times its height, right? Because it's any volume of a shape that's not like a pyramid is really just the area of the base times the height. Okay, so the height, again, this is going to be dx in our integrals. The area of the square is what we got to figure out. Okay, well, area of a square is just like base times height, or is like side squared, right? Well, that distance would be the distance between y equals 1, so this upper line, minus my curvy wall. 1/3 minus 1. Okay. My height, again, is my dx. Oh, but it's area of a square, so we're going to go ahead and square this, right? Because, like, area of a square is the side squared. That's essentially my volume. Our integral goes from 0 to 8, and we're integrating with respect to x. dx is that height. Here is those areas. So it's the sides of my squares squared. And all that's left to do is add them up, right? So we've cut this piece into infinitely small square. We've cut this solid, I should say, into infinitely small square slices, and we're adding up their areas. Again, I'm mostly expecting you guys to be doing these on your calculator. I'm not going to solve these step by step. You don't need to. You should get 3.2 in this particular case. Okay, let's look at another example. So what we will see is that our integral depends on the shape of these cross sections. So it doesn't have to be a square. Here it says isosceles right triangle. So isosceles right triangle has the property that, then this is going to be useful, so base times and height are equal, right? So base is equal to height, so really this could be like, I don't know, base, and then the area would be just 1/2 base squared, right? So the reason it gives you that is because the calculation is a lot easier than if it was just any triangle, because we'd have to worry about the changes in the height as well. Okay, so isosceles right triangle with a leg in the region R. This sounds really hard to imagine. I'm going to pull up the animation. These on Delta Math, I love these. Like, I learned these out of a textbook that didn't have any animations. So look at these. It's really helpful conceptually. So as I drag the slider a little bit, it populates those triangles, right? So here, this could also be like a hallway or something like that, or some kind of solid that you're designing. Here's what the solid looks like, okay? So obviously what I'm doing is finding the area of each triangle and adding them up infinitely thin slices until I get the whole volume. Now, this base is what we need to figure out. So we're going to use the formula. We're going to integrate 1/2 base height, but it's really going to be 1/2 base squared, right? Well, from my graph, it looks like my linear function is below my natural log function. So that base is going to be the natural log function minus 2 minus the linear function. Okay, so that's the distance along the bottom of that triangle. And then we're going to square it. Okay. And now, the bounds here are ugly, right? So to get these numbers, they're ugly because it's a natural log function. Almost pi there. To get these numbers, we need to set ln x minus 2 equal to x minus 4. Okay. To solve that, you use the solver on your calculator most likely. If you go back to the most recent calculator lesson, if you skip that, that will help you tackle these. Okay. Doing most of the problems in this lesson are doable by hand, but particularly these problems where natural log shows up, you're going to want to use the solver on your calculator. Here's my integral though, and these are the intersection points. This is the base of my triangle. 1/2 comes from my area formula. Dx is the height. And again, I would solve that using a calculator in this case. We'll look at one more. So the rectangle ones in this lesson are the hardest ones. Okay, so here we have rectangular cross sections. Height is twice the length of its base. Okay, so we have area is base times height for a rectangle, right? We know that height is actually just 2 times the base. So area would be 2 times the base squared. Okay, so that should give you a big clue on how to set this up. My integral is going to be essentially the same. Here, mercifully, they gave us the bounds, so from 0 to 2. And then looks like e to the x is on top, minus -3 is on the bottom, squared, and then we need to throw in that 2, right? And then dx is my height, and then you continue to solve. Okay. So in the rectangle type problems, they give you the relationship between the base and the height. Make sure you're clear on how I set all 3 of these up before you proceed. I think this is the hardest lesson in the unit.